Hello, and welcome to the RETHINK live event, which is how hydronic balancing helps heat pump system deliver year-round efficiency, brought to you by Danfoss Climate Solutions. My name is Andrew Simpson. I'm one of the national OEM sales managers, and I'll be leading the session. If you have any questions along during the session, please drop them in the Q&A blocks on the On24 platform. The first thing I want to talk about is the overview of trends and regulations that are driving the development of products and solutions in the HVAC market. So we're seeing a couple of mega trends. The first mega trend is decarbonization. This is something we're seeing globally. And really what that means is that we're converting fossil fuel sources to renewable energy sources. And that's really driving a strong initiative to move towards heat pump technologies and heat recovery. Another mega trend that we're seeing is digitalization, right? So we hear all about IoT and trying to make everything part of the web and trying to drive highly efficient solutions through digitalization of main products. So some of the other things that are driving the market are regulations. So we see, eco-design for reducing indirect CO2 emissions and increasing seasonal efficiency performance requirements. An F-gas phase down. So this is more of a direct CO2 emissions and reducing the GWP, global warming potential impact of refrigerants in the market. The other thing that is changing the market is the indirect CO2 emissions driven by ASHRAE 90.1 and the Department of Energy for changing of seasonal and full load efficiency. So full load like EER, chiller efficiency, COPV, part load efficiency like IPLV, etc. The other thing that we're seeing is a big change with the Infrastructure Acts, the AIM Act and the EPA Act, driving CO2 emissions through changing an HFC phase down through the AIM Act as well, moving to lower GWP solutions below 750 and HFC phase down requirements. As we know that local legislation is also driving the demand for energy efficiency buildings. We've seen things like fossil fuel phase downs in places in the West Coast in California. And this journey to net zero buildings, both multifamily residential and commercial buildings, requires a clear focus on complying with local legislations and restrictions while delivering energy and cost efficient HVACR performance. So there are three pillars of energy efficiency in any building. The first thing is the envelope, right? Meaning on the construction side, we're going to look at materials to construct these buildings to have better insulation and better thermal efficiency. You see things like reflective paint, all different ways to construct a building to make sure that they are more energy efficient across a wider range of climates. The other thing we're looking at is, other pillar, is energy generation and supply. This is sustainable energy sources. So moving away from coal burning plants to heat pumps, district energy, renewable energy sources, wind, solar, etc. And there's a third portion of it, which is the demand side of it. So we need to work on making sure that our buildings are using the energy that we're generating in the most efficient manner. So optimizing the building with automation and control systems to gain the most optimization and efficiency from these renewable sources of energy. So how do we do that? We use hydronic balancing to help heat pump systems deliver year-round efficiency. Heat pump systems are a key driver in making it possible to utilize renewable energy in a commercial and multifamily residential buildings. Today's heat pump systems often consume more energy than expected. And the challenge for that is that the heat pump systems are not performing to their full potential. Their energy consumption is higher than expected, which is really not giving us the return on investment that we need. And the main reason for this is the secondary side of the system has a lot of dynamic factors. So it's not just the heat pump itself, it's how the heat is being used in the building. The big cause for this is pressure and flow changes that deviate from the original system design. The solution for that is having a dynamic hydronic balancing. And what that does is it stabilizes pressure and flow deviations to improve the efficiency of the entire heat pump system, essentially increase the envelope of design conditions that the heat pump can operate in. And what that also does is it's going to improve our reliability. It's going to extend the heat pump system's lifespan and optimizing the flow. Hydronic balancing, we found, is essentially required for complete system efficiency. It is the key to establishing proper indoor comfort while maintaining energy efficiency system operation in all climates and the entire year. Dynamic hydronic balancing valves address the root cause of unanticipated pressure fluctuations that cause the system imbalances and uneven water distribution. So stabilizing the pressure and flow conditions with hydronic balancing sort of works very similar to this. So like you have a garden hose. If you take a garden hose when you were a kid and you stretched it out and you turned it on, and water is going to flow at a set rate and a set pressure. When we don't have any balancing, as pressure changes in the house, someone flushed the toilet, runs the washing machine, that flow goes up and down. Or if you were to put your thumb on it and you were to increase the pressure is going to increase and it's going to go farther, but you're going to send less water. So when we look at a full load condition, which is typically how we've designed our static hydronic balancing, that's the single condition that our balancing is going to work at. And dynamic balancing is going to do the same thing that the static balancing is going to do in the same condition. It's going to work in the same way. Where dynamic balancing has a tremendous difference is when there's a partial load. And then it's essentially what a pressure independent control valve does is manage the flow and pressure as if your thumb weren't there, and the requirements for water can vary across a wide number of conditions. And this is how we cope with deviations from the original system design, right? So to take it a little step further, that when we design a heat pump system with a building, the supply water is designated for the absolute worst possible condition, the lowest outdoor temperature, 50 degrees C, water at 10 degrees C ambient. And there's some weather compensation to that, right? So the supply water temperature and pressure is going to follow the outdoor temperature, right? And on an average, it's not at these worst case conditions. On the average, it's going to be lower than that, right? So it could be we may need 36 degree water C at plus 3 degrees Celsius ambient, right? And in that case, we're going to have an unbalanced condition. When we're unbalanced, we're going to reduce our system efficiency, and we're going to have requirements for increased flow. With dynamic balancing, in real world conditions, as you can see here, at that part load condition, the flow and the pressure is going to be met, at the same time reducing our flow requirements at the site. How did we know this? How did we prove it? So we have the world's first facility to test indoor climate system. This test center can control and monitor both energy generators, so heat pumps and gas boilers, and heat emitters as well. So radiators, floor heating, basically simulating the entire condition that you would have in a residential, or multifamily commercial building. The heart of the test center, what we do here, the secret sauce, is to making sure that we're getting the control system of the hydronic system and then the data acquisition system. So the conditions that we tested in this climate control chamber was we did some static balancing and we did some dynamic balancing to sort of prove the benefits of different loads in different rooms and different conditions, as we can see here. When we compare differential pressure and flow, and once again, back to the hose, right? You can see on the static balancing, we have these big spikes of flow and pressure. It looks like, driving over moguls or a bunch of speed bumps, right? And with the dynamic balancing, it's a much smoother surface. It's a much more consistent flow. It's a much more consistent pressure across a wide range of conditions. And that also, what that means is that at that 50% load, we're going to get better performance, and we're going to have fewer changes to the conditions to the heat pump itself. Once again, flow stability, right? And we want to make sure that our entire hydronic system, including the heat pump itself, has the least amount of variation to it. So static balancing, we are seeing flow variations from 0 to max flow. Think about getting in your car, turning on the ignition, putting it in drive, and putting the gas pedal all the way down, and then when you see a stoplight, taking your foot off and slamming on the gas at the same time. It's not how things work in real life. With dynamic balancing, the flow variations is from a low to medium flow, which is how we drive in a 35 mile per hour zone every day of our lives. Conclusions that we can draw to the test. Dynamic balancing proved to eliminate a lot of our differential flow and pressure fluctuations. And we have a stable flow under all tested conditions. And really the benefit of this is that we saw reduced supply and return temperatures, and that allowed us to increase our energy efficiency in the entire system by 10 or 15%. And that's where the the proof is. So improving the entire heat pump system. So in addition to talking about balancing, we have to look at the heat pump itself. And like any vapor compression system, we have a set number of systems. We have a compressor, we have a hot side heat exchanger, we have a cold heat exchanger, and we have a metering device or an expansion valve. And a heat pump or reversible heat pump, the refrigerant can move one or both ways. And when we have flow stability on the heat pump system, that means that the fluctuations when we're on and off are more stable, all right? And because of that, we're able to modulate our heat pump in a narrower range, giving us improved system efficiency and increased reliability. So at the end of the day, what does this all mean? It means that we're able to create a 20% savings on the seasonal coefficient of performance. And the reason how we got there is that we have a 10 to 15% improvement in energy efficiency with the reduced in supply temperatures for the heat pump, and a 2 to 5% improvement in energy efficiency with the stabilized water flow, both on the heat pump side and on the pump side as well. The third part about that is that because we're not cycling the heat pump on and off as often, we are getting much more life and reliability out of our heat pump. How do we get sustainable energy sources? Well, we can do that by any number of ways with Danfoss scroll compressor products, variable speed products, turbo core compressors, our specialized microplate heat exchangers and variable speed drives, other line components. And on the hydronic side, we've got the hydronic balancing control valves, floor heating valves, radiator heating, etc. Dynamic hydronic balancing is the key to developing future-proof heat pump systems. And as the demand for greener, more energy and cost-efficient buildings increases, utilizing dynamic hydronic balancing will ensure a future-proof heat pump system that will get you to your decarbonization goals. So let's have a look at some of the questions from our audience. The first question we got is, thank you for a great overview. Can you please give some insights into the challenges brought by using such a system? Are there any downsides? I think the downside of using a system, and I'll start with that first, is that it's a shift in paradigm. It's a change in thought paradigm. So we've always designed things for the worst case scenario in a static condition. So we have to go out there and change the thought and the mindset around it. But as far as a technical perspective, having a heat pump operate in a wider envelope of conditions, and we've seen climate change, and we've seen a change in conditions, especially across the United States, where the weather and water temperature can vary more than it has traditionally. Having a building operate in a wider range of conditions, I think, only can bring upsides. Just the downside is getting people to change their mindsets around the use of dynamic hydronic balancing. Let's move on to our second question. How feasible is it to implement such a system? Are the current market trends in North America supporting this type of heat pump system? Absolutely. I think that moving towards heat pump building optimization is a primary focus for just about all the building owners and commercial builders and the OEMs in the heat pump market as well. It's very feasible to implement such a system. Working with design engineers on new construction obviously is one of the easiest ways to do that, and I think that's where we're seeing the market trend move. But also looking at existing buildings. We did a study here in Baltimore with a hotel that had some significant hydronic imbalancing a couple of years ago, and we found out that moving towards a dynamic balancing situation was ways to not just increase their efficiency and increase, decrease the amount of cost that they were using their heating system, but also increased guest satisfaction with the hotel to make sure that their domestic hot water and their climate system inside the room was more consistent. As a building owner, what immediate and long-term benefits can I get from using pressure-independent controls versus pressure-dependent controls? So, obviously I think that there's a small cost difference from going from a basic pressure-dependent control to a pressure-independent control because we have to combine it with a building automation system. But the cost savings, both immediate and long-term, would be significant. In addition to that, depending on the structure, whether it's a multifamily or commercial building, a hotel, office building, having clients and stay for longer periods of time, or better guest satisfaction, or having tenants able to use less energy to heat and cool their homes, I think has an immediate effect, obviously, but it's also going to have a long-term effect on the economic viability of the commercial building. What sort of buildings is Danfoss using pressure independent controls in? So I mentioned we have a building here in Baltimore, a hotel that's using that, and that was a retrofit building. The Burj Khalifa in Dubai also is another building that uses Danfoss ABQM pressure independent control valve. So wide spate of buildings in the commercial and multifamily residential structure as well. For the questions that we left unanswered, I'll get back to you shortly. Now for some final words before we wrap up. If you want to embark on this journey to net zero, it's possible to start today. If you're ready to start down the path to net zero, reach out to your Danfoss account manager. Thank you for your time today. I've been Andrew Simpson for Danfoss RETHINK Live.